All right, good afternoon, everyone. So we're going to get started on the first real lecture about machine learning. We're going to start super simple, and we're going to find that in this really simple case, we can gain some intuition, and we can solve problems really easily, and then we'll get more realistic as the semester goes on, basically. So each of these, so the course is organized into different units, and each unit has a set of lecture slides, it has a demo, and a homework, and a lab, and a quiz. And so in the lecture, we often start by just talking about the demo and the machine learning problem we're trying to solve, the application in that lecture. So in this first lecture, the task is to predict automobile fuel efficiency in miles per gallon. And so the code is in this Jupyter Notebook, which you can find on the main course GitHub repository. And so basically this notebook, as we'll see in just a moment, it starts out by loading data. It gets it from OpenML. OpenML is a site that has just tons and tons of data sets. You can often get the data files from different sites too, but for a lot of our demos, we're just going to get them from here. And the first thing we're going to do is we're going to load them into what's called a Pandas data frame. And the Pandas data frame is just one of the most common ways of storing data, like the way that you store it when you first load it. And I'll show you why. It has some nice features. It also can do nice things with like filling in missing data, things like that. And so this data frame, a Pandas data frame is an object. It's an object in the sense of object-oriented programming. It has, that means that it's an object with data fields as well as functions or methods attached to it. So it has many data fields, but the three main ones are the values, which contain the numerical values of the data set, the columns, which contain some text labels, so you know what those different things are that you're using. In this case, we'll see what they are, as well as .index, which is the row label. So columns in this case, so this is sort of an example of what you get when you print out a Pandas data frame. So here, every one of these rows is a sample in the data set. And essentially, these are the things, the features or attributes that we're using to do the prediction. So here we're trying to predict miles per gallon fuel economy from these things. And then this over here are the actual miles per gallon for, let's say if you're talking about row 0, then the miles per gallon for that car was 18. Row 1, it was 15, and so on. Okay, so let's step back a little bit. So the first thing you do in a Jupyter Notebook is you typically import the libraries you're going to be using. And typically you abbreviate them just so you don't have to type as much. So some of the main things we're going to import at first is this Pandas library, which I've been talking about, and also NumPy. NumPy, as I mentioned the other day, is like the numerical processing library in Python. It has a lot of commands similar to MATLAB, but not the plotting stuff. A lot of linear algebra, a lot of basic statistical type thing like mean, variance, all that stuff. So we'll be using that a lot throughout the semester. So the way that we actually download this data is we import this command fetch OpenML, which is a way of talking directly to OpenML. And we have to tell it what is the data set you want to download. So we're going to specify the name, which is AutoMPG. It turns out there's 3 versions of that data set on OpenML. We want version 1. And this one, as frame equal true, means we want it to be formatted as a Pandas data frame. So I should be a little bit more specific in that this outputs this AutoMPG, but AutoMPG is actually a structure with 2 main fields in it. One is what it calls the data, which are these things we're using for prediction, and the other is what it calls the target, which is the thing we're trying to predict. So those are two separate fields. So this one is a pandas data frame, and this one is what's called a pandas series, which is basically a pandas data frame with a single column. Okay, so that's what we have here. And if we look at this, what is in here? So each one of these refers to an automobile. You can see how many cylinders in the engine, the displacement of the engine in cubic inches, the horsepower, the weight of the car, the acceleration. I think that's seconds, 0 to 60, the year it was built, and I don't remember what origin means. But the question then is, can we predict like this 18 miles per gallon from this data? So that's sort of the objective of this unit, except this unit is very simple. It's called simple linear regression. What we mean by that is that we're only going to use one of these things, one of these features or attributes to predict this. So we're going to see, well, what if I try to predict that with displacement? What if I try to predict that with horsepower and so on? And then the next unit, we'll use multiple. Okay, so we're just trying to start simple, just to build intuition, keep everything simple, and then we'll make things more complicated as the semester goes on. Okay, all right, so the first thing you typically want to do when working with a data set is somehow visualize it. Make sure it's as you're expecting, make sure there's nothing terribly wrong. Sometimes the data, the way it's formatted, might be unfamiliar to you. You might make an assumption, and then what you get is just complete garbage. It's often easy to notice that happening when you just try to visualize the data. There's different ways to visualize it. We're going to often in this course use the matplotlib library. This is a library of plotting routines that are very similar in syntax to MATLAB's plotting routines. So if you're familiar with MATLAB's plotting stuff, that's exactly what this is replicating, but in Python. So here's how we import that library. We abbreviate it, or abbreviate a portion of it as PLT. And then all of the plotting commands will be plt.something. And so then this is what we're going to do to extract a particular column here. So we're going to say, let's look at the displacement column. So the way to access that particular column of a pandas data frame is you can just, in square brackets here, you can pass in this string, and then it will extract just that column. And then the next thing we're doing is we're casting that as a NumPy array. And so again, NumPy is the main format for data processing in Python. So this data frame is really, pandas data frame is really nice as just a way to initially load your data, maybe deal with filling in missing values, maybe visualize it here. Like we can just notice a few things here. This is the first 5 rows, this is the last 5 rows. You can immediately see that there's 398 rows. So notice, even though it says 387, we're actually starting at 0. That's one thing about Python, you always start counting at 0. MATLAB, start counting at 1. Okay, they're different. So you can see how many samples are in your data. You can see, what you're using for prediction. Get some intuition. So some of these things are floating point numbers. Some of these things are integers. In other data sets, some of the things could be strings. So Pandas is very capable in dealing with heterogeneous data. Okay, so here we've extracted the displacement numbers into a long vector x, and we've taken our target, miles per gallons, and we've put those in a vector y, and then we're going to plot them, and we're going to use what's called a scatter plot. This is the typical way you plot data. You plot each one of the samples as a point. So because these are just now, x are scalar values, y are scalar values, we can just plot this in a simple 2-dimensional plot like this. And we do that by using this matplotlib command scatter. You just say scatter the x vector, the y vector, and it plots this. Then we can make it a little bit more interpretable by adding the x label, adding a y label. So this is going to be x, this is going to be y, but you can see here that they really mean displacement in miles per gallon. And we can plot that grid, which makes things a little bit easier to view. So that's what we have in terms of visualizing data. And these are very common things we'll be doing in almost all the demos, all the labs. All right. So now let's step back, and this is exactly the scatter plot that we created on the previous page. But we could repeat that procedure and make a different scatter plot of horsepower versus miles per gallon, or acceleration versus miles per gallon. And so, as you can see, we get some different plots. So here, let me ask a few questions, and I'm going to just call on you at random. And this is kind of my way of taking attendance. So let's see, is Yu Yao Fan here? Okay, great. So just using kind of whatever intuition you might have, which of these do you think would be the easiest to make the prediction? The middle one. Okay, and why? What's your intuition as to why that is? Just in words. Doesn't have to be precise. Okay. That's okay. Let's see. Is Shifatul Islam here? Okay, what do you think about in terms of, like, would you choose the middle one, and why?
I think the first one and the second one.
Okay, and why would you like to use those?
There is an apparently inversely proportional relation between the displacement and the MPG, and at the same time between the horsepower and the MPG. But when it comes to acceleration, there is completely random relation, so I don't think I can extrapolate very many things on it.
Yeah. Okay. Great. Yeah. That I agree completely. So, as we go through the course, we'll be developing more sophisticated models in order to capture these relationships, and in some cases try to learn those models directly from the data, so we don't have to use our human intuition like you did. Okay. So great. So now, even though this data, I agree with you that it seems to have some sort of inverse trend here. We're going to use linear models. We're going to focus on linear models in this unit, basically because they're really easy to work with, and there's a few other reasons. They're actually, in some sense, the basis on which you can build a lot of other models. Because, for example, even though this looks like it has an inverse relationship, you could pre-process the data by just inverting all your y variables. And once you do that, you would get a new data set that would then look linear. And then you can just use all the linear methods we're going to be developing. So even though the linear methods seem like maybe kind of weak and limited, if you allow pre-processing or sort of another processing stage, then they become just as powerful as your preprocessor is. So, and this is actually, when we get much more advanced and we're looking at these deep networks and stuff, essentially you can think of them as at the end doing something linear, and then all the other stuff is just pre-processing the data in the right way so that that linear problem is solved well. Okay. So those are the reasons we're looking at linear, but that's what we're going to be doing. So let's establish a bit of notation, and this is going to be notation that we're going to use throughout the whole term. So we're going to see this notation, and also terminology. The terminology is important because even though I'm going to try to stick to certain terms here, if you go and you read other sources, whether they're papers or blogs or whatever, data set descriptions, you might see completely different terms. And so if you don't understand what those terms are, you have no idea what's going on. Okay, so to start, the thing we're trying to predict, which I had called the target, I'll often call that the target or the label. That thing, we're going to always call y. Okay. In this particular unit, this y is just a scalar. It's just a single number. Okay. It's the miles per gallon. That's what it is. Later, it could be a vector, but for now, it's just a scalar. Similarly, we're only using a single quantity for prediction. We're going to call that x, and in this unit, that is also just a scalar. Later, it will be a vector. The name I'm going to use usually for this thing we're using for prediction is going to be the feature. But you can see there's a lot of other terms: predictor, regressor, attribute, independent variable. For the target, we have also, you can call it the label, the regressand, the response variable, the dependent variable. Okay, so these are all things that, even though I'll try to be consistent to be, simplify the delivery, it's important to know these other terms. Okay, now the data set that we're given in this sort of a problem, this prediction or regression problem, is a set of pairs, x, y pairs. And we're going to put a subscript I on those variables to indicate the index within the data set. And we'll refer to each of those pairs as a sample. So we have a data set with many samples, and we're always going to use n for the number of samples in our data set. Okay. And then this scatter plot we've seen before, that's the name we give to that kind of plot that we use to visualize these pairs. Okay. All right, so now let's get to the model. So we said we're going to focus on linear models, so let's be a little bit more concrete about that. So here we have a data set on the right. You can think of the blue points as the scatter plot, and you can see this particular data set does seem to have a nice linear trend. Okay, and in fact, that red line there, could be a very good guess of what that linear trend is. So how can I describe that red line mathematically in terms of the variables we're dealing with? So here we have, on the horizontal axis, we have x. On the vertical axis, we have y. And now note that I'm going to use the variable beta 1 for the slope, beta 0 for the intercept. And there's sort of different versions of y. There's y as a general quality, a general quantity like a variable. There's the yi's, which are all those little dots. Actually, the dots are really an x-y pair. So let me denote what I mean by yi there. Yi is really just the vertical value. And then y hat is actually this. That's the prediction. That's a function of x. That's the red line. So the question then is, how can I write y hat in terms of beta 0, beta 1, and x? And so I will pose this question to Asa Lanning. Is Asa here? Okay, yeah. What do you think? Can you give an equation? We want to fill in the blank right here. So you have slope and intercept. What do you think? X is the independent variable. X is the thing we're using for prediction. Not sure? It's okay. It's okay.
Yeah, I'm just confused with the question.
Okay. Let's see. Noah Ludwig. Is Noah here?
Yeah.
Yeah. What do you think? Any idea how we write this with beta 0, beta 1, and x? How we write that equation for y hat, which is the red line?
Beta 1 times x plus beta 0.
Exactly. So it's, I'll write it beta 0 plus beta 1x. So that is our linear model. So pay attention to a couple of things here. So on one hand, we're defining this quantity as y hat. So this little triangle above the equal sign indicates that this is a definition. Okay. So I'm not trying to prove to you that y hat is beta 0 plus beta 1x. I'm just defining y hat as beta 0. I'm just giving it that name. Okay. On the left side, though, notice we have an approximate equal to. So this says that the true miles per gallon is not exactly equal to this. It's approximately equal to that. That's sort of the assumption or the proposition for this data set. So it's important to notice the difference here with the equal and the approximate equal. Okay, so that's one way of writing the model. As I mentioned the other day, we're going to be using a lot of linear algebra, so we're going to often be collecting things together into vectors and matrices. So here we're doing it for the first time. we have two parameters of our model. So what are the parameters of our model? Let's see. Hao Chen. It's Hao here. Okay. What about Dion Chen? Yeah. What are the parameters of our model?
So the parameters,
Yeah. What are the parameters?
I think just use the slope and intercept.
Exactly. Slope intercept. So beta 0 and beta 1. Those are the things that we can choose in our model. Those are the parameters of our model. So we're going to put them together into a vector, and that's what we're doing right here. And so the thing I want to point out here is that this is a bold quantity, and these are non-bold. So all throughout this course, I'm going to be using bold quantities whenever we have matrices and vectors, and non-bold when we just have scalars, just to try to make things a little bit easier to parse. So, and also, when we have a matrix, it's going to be a capital bold letter, and when we have a vector, like a single column of a matrix, that's going to be a small case bold. Okay. So that's why we have beta as lowercase bold. The other thing is I'm always going to have our vectors be defined as columns so that you don't have to wonder whether they're rows or columns. You just know that they're columns. For that reason, so another way I could write this beta here is I could write it like this, beta 0 on top, beta 1 on the bottom. But often it's harder to do that when I'm typesetting these notes. So here, notice I'm putting them as a row, but then I'm transposing them. So this transpose turns this row into this column. Okay. Now, if I ever needed to make beta into a row, maybe I need to do that as part of some larger equation, then what I would do is I would take beta and I would transpose it. And now that beta is actually a row. Another thing is when I write things, it's hard for me to make things bold. So when I'm writing on paper or on these slides and it's a vector or matrix, I'll put an underline on it as a way of saying that's like a bolded quantity. Okay, so this is my beta with the underline. That's the bold beta. Okay.
Why'd you say you were bolding them?
Just to make things easier to parse, so that when you look at an equation, you immediately know what are matrices, what are vectors, what are scalars. It's not commonly done in some fields, like in mathematics, it's not commonly done. In electrical engineering, it is commonly done. So, because I was trained, I have my degrees in EE, that's what I'm used to doing, and I personally think it makes life a lot easier when you read something, you just know this is a matrix, this is a vector. You don't have to hunt for the definition somewhere else to try to figure out what's going on. Okay. All right. So, yeah, and so why are we using this model? As I mentioned before, it's easy. It's easy to interpret, it's easy to analyze, and as we'll see, it's easy to optimize these parameters, beta 0 and beta 1, to find the absolute best ones. So we talked a little bit about, when is this a good model? I think people basically tried to explain informally that, you kind of want, for whatever model you have, you want that your samples are near the model, right? That's kind of what you want. You don't want a samples really far away from the model, because then it seems like the model's not really accurately describing your data. We're going to, a little bit later on, we're going to come up with much more quantitative, explicit definitions of, when is it good or not. We'll come up with a single number that tells us how close, how good or bad of a fit it is. So we'll be more specific. All right, any other questions on this slide? Okay, a bunch of important things here. Okay, great. So now we're going to start talking about how we actually determine these parameters. So, all right. Let's see. So let's first rewrite our model. Okay. Lukman Oyelami? Yes. So do you remember, what do I fill in the blank here with for our model? How did we write y has approximately equal to other stuff? Exactly, thank you. So that's our model. There's that approximate sign, meaning like, you know, this is an approximate model. But the approximations are vague, so let's be more explicit. Let's write this with an equal sign, but then with one more variable to take up that error, that slack. And that's going to be epsilon. We're going to call that the residual. And so graphically, let me set up some notation again. So this is going to be yi. This is going to be xi. I'm focusing on this particular point here. Y hat, we said, is that red line. So can, let's see, is Javier Perez here? Okay, so Javier, how can I draw epsilon I? What is epsilon I on that graph? The distance from what to what? Okay, from y hat to what? Yes, exactly. So so this distance from the line up to here is that epsilon I. Okay, so we have the residual is the vertical deviation from the point to the regression line. So basically, other ways to think about what we're doing is, remember we have this equation for yi hat. That's like the same model equation, but remember we have like an equality version. We can write this as equal to y hat. Y hat is approximation. And now if I'm talking about particular data points, then I put subscripts I on here and here. So I get xi, y hat I. Okay, and now you can see that I've defined, you know, I can also do this with yi. I can put a little I here, a little I here, I here. Now you can see just from those equations what we said on the graph, which is that epsilon I is the deviation between yi and the approximation y hat I. Okay. So now that we have this concrete definition of this residual, do we want the residual to be big or small? Sean Starrett, you here? Yeah, small, exactly. How do you think we should measure the size of it? I'll give this to Chanwoo Son. Yeah. How can we measure the size of epsilon I? And there's several answers to this. Yeah, how do I, so we said we want epsilon I to be small. How do I define small? Like near zero. Okay, how do I measure the distance between it and zero? There's different ways. So could it be squared error, absolute error, cubed? Okay, yeah, that's good. The main point is that there's actually different definitions. I could say I want the squared error to be small. It's actually different than saying I want the absolute error to be small. If you focus on squared error, because the square increases very quickly as things get large, that means and squared error near zero is almost nothing, right? If you think about squared error, if I have a parabola here, near the origin, it's tiny, but as I get far from the origin, it gets incredibly large. So squared error says, I care about errors not being really big, but if they're really small, I don't really care. Absolute error would look more like that. That actually penalizes small errors much more, but doesn't care as much about big errors. So that's why it actually matters how we define small. Like, do we define small in absolute sense or squared sense or some other sense? Exponential, logarithmic, there's many choices. So that's what we're going to focus on. We're going to focus on the sum of squares because we have many data points, right? So I'm going to look at the squared error for every epsilon, but I actually want to look at all the data points. So how, just based on this name here, sum of squares, how would we write an equation to fill in this blank? Let's see, is Ines Arda? Yes, did I pronounce it right? Enes Arda, sorry. What do you think about, just take a guess of how we can write an equation here.
So it's sigma
Okay,
yi hat minus y hat in parentheses.
Okay.
Square.
okay,
Yeah, that's it.
very good so far.
Yeah, I from 110.
Perfect. Okay, that's right. So this is the residual sum of squares. So remember that this is my epsilon I. So you can see it's just the sum of the epsilon I squared. But I like that you actually wrote it in terms of yi and yi hat. So that's exactly right. So that's what we're going to say is our objective. That's what we want to minimize. This is our loss function. Like I said, we could choose other things. We could choose a sum of absolute values. But it turns out that this is the one that's easiest to analyze and work with. So it's also, I would say, the most common one, partially because it's the easiest. It has other names. Sometimes it's called the sum of squared errors. Sometimes it's called the sum of squared residuals. We'll call it RSS. And then notice also here, I wrote it in terms of the parameters beta 1 and beta 0, which are the things I can't adjust. But it might be weird because I'm not writing those on the right side of the equation. Just remember that these things are really, they determine y hat I. Y hat I is a function of those things. So as I adjust those, I can adjust my y hat i's. I can make my RSS smaller. Okay, and this is a problem that maybe many of you have seen before. This is the least squares fit. This is just a least squares fit. And can anyone, let me ask, let's see, is Sajad Akarati here? Can you explain, based on this plot, what is RSS trying to minimize? Like if you had to explain it just visually in terms of the plot? You know, the idea is if you imagine all of these little errors, there's sort of an error for all these points. You're trying to adjust beta 1 and beta 0, which is the slope and the intercept, until the sum of those squared errors is as small as possible. So, you know, you're probably going to care about the ones that are farthest away most, because since they're farther away and you're squaring them, they have the biggest effect. Okay, so that's, yeah, I think it's important to sort of just intuitively understand what we're doing. We're adjusting the slope and intercept of this line to try to make all those deviations small as possible in this sum square sense. Okay, so if we step back and look at what we've done, we've done something which is actually an example of a general recipe that you do in machine learning and refers kind of to what I talked about at the end of last lecture. So we assumed a model with some parameters. For this unit, this is going to be the simple linear regression, so it's a scalar linear model like this. Then we went and we got a bunch of training data. In this case, it was like that auto MPG data set. Then we defined a loss function, which is in this case the residual sum of squares. We know what it means here now. If I say beta 1 and beta 0 are like the best or good or bad, it's all about how small they make that quantity. And the very last step we are yet to do is to figure out what exactly are the beta 1 and beta 0 that minimize that RSS. That's the task ahead of us. And it turns out that this is really something that you do for many other machine learning problems. You pose some model. It could be completely different. It could be complicated like a deep convolutional neural network. You collect some data set. Maybe it's gigantic. Maybe it has millions of samples. You define some loss. That will depend on whether you're doing regression or classification or something else. And even then, you have many choices. And finally, you have to do this optimization. You have to try to figure out what are the parameters that minimize your loss on your data set. That's what we're doing. We're just doing the simplest version. Okay. All right. Any questions? Okay, great. So So it turns out that for this problem, and actually a lot of problems, statistics are useful to get some intuition about what's going on. And statistics are basically just ways of summarizing data. That's what a statistic is. It's a summary of data. There's many different ways you can summarize it. And so we're going to get into some of the simplest ways you can summarize data, down to just a few numbers. And what we're going to find is that our beta 0 and beta 1, the optimal values, are just a function, a relatively simple function of those simple statistics. If we can compute those statistics, we just plug them into a couple equations, and we find the optimal betas. Okay, so let's talk about sample mean, sample variance, and standard deviation. So I think these are things you've all seen before. So let's see. Zachary Boyd? Zachary here? No? Okay, what about Logan Brown? Yes, Logan. Do you remember the definition of sample mean? And so here we're thinking about the xi's in my data set. How do I take that set of xi values and compute the sample mean?
So the sum of all the xi's over the amount of xi's.
And what is the amount? Remember, we're using the same variables all throughout the semester. Anybody else? Let's see, is Jiajuan Kai? Do you remember?
Actually, it's Thai. Sorry.
So what, how do you pronounce it?
It's Thai.
Tai.
Thai.
Tai.
Forget about it.
Okay. So how many data points do we have?
Actually, I think it's from 1 to n.
N, exactly. Okay. Right, so we have, I'll write it like this. 1 over n, sum of all of our xi's from 1 to n. Okay, so it turns out for yi, it's the same thing. It's just we have the y's instead of the x's. What about sample variance? This is a little trickier. Let's see. Jake Hedrick. Is Jake here?
Right here.
Yeah, what do you think? Do you remember that formula for sample variance?
Not off the top of my head.
Okay. Let's see. What about Chaewon Lee? Yeah, what do you think? Sample variance.
As the summation of xi minus x bar squared. I mean, square outside of the bracket.
Okay.
Like n divided by n or n.
Exactly. So there's actually different ways that people define the sample variance. In particular, like sometimes you divide it by n, other times you divide by n minus 1. We will talk in detail about that in Unit 3, but for now, we need to use the 1 over n, which is known as the biased version, for all our equations to work out. So that's what we're going to use. We're going to use 1 over n. And so essentially what we're looking at here is the difference between each data point and its sample mean. How far does it deviate from its sample mean? And then we're looking at the sum squared of that. Sum squared deviation from the sample mean. That's what the sample variance really is. And we have the same thing for y. So here we have to subtract y bar, which is the sample mean of y. Okay, and so just some intuitions here. We have, one more thing. The sample standard deviation, let's see, is Robert Renard here? Yeah. So do you remember what the standard deviation is relative to the variance?
It's the square root of it.
Exactly. It's just the square root. So that's just going to be like Sx, Sy. Notice that over here we actually put a square on there, so I'm just removing the square. Okay. The nice thing about the sample standard deviation versus the variance is a squared quantity. So, the units are kind of weird. If we're dealing with miles per gallon, then variance is actually like miles per gallon squared. But standard deviation has the same units. So it's easy to visualize and think about what it means. So here we have an example of 2 data sets. We have some histograms. And so basically we have a bunch of bins, and we have, like in this particular bin, you can see there's 300 and some and so on. So basically from this data set, you could compute a sample mean. It turns out that, well, I don't know exactly for this data set if it's 100, but it looks a little bit skewed. But basically the sample mean is like the center of this, and the sample standard deviation is going to be the width of this. And so the blue one and the red one here have the same mean, but the standard deviation of the blue is much bigger than the standard deviation of the red. Okay. All right, any questions on anything here? Okay, great. So, yes?
Is that the square missing?
I missed the square, thank you. There is a square missing there. Okay. Okay, so here's our data for horsepower versus miles per gallon. And so in this case, the sample mean of X is, what would you guess if you just had to take a guess of this? Remember, X is this way, Y is this way. So let's see. Kevin Donnelly? Is Kevin here? No. Okay, what about Andre Quattle? Maybe?
Here.
Yeah. What do you just take a guess.
What was the question again?
What is the standard deviation of, sample mean of X?
Maybe like 100?
Something like that, yeah. So it's kind of like the center of mass in this direction. So it's like where, if you just sort of compress all these points down so that they're sitting on this line, and imagine where the line is going to balance. That's essentially the sample mean. So X, sample mean of X, I'm guessing maybe around there. What about the sample mean of Y? So let's see, is Dominic Alexander here? No? Okay, what about Anshul Amin? Yeah. The sample mean of Y is around 27. Okay, yeah. Maybe something over here. If I had to guess, actually, maybe I'd put it a little lower, but we'll see in just a next slide or so. And what about the standard deviation of X? If you just had to take a guess, I don't know. Maybe, I don't know, I'm guessing maybe something like that. So here we would have Sx on either side of this. So like from here to here is, oh, actually, that's probably bigger than that. But this is something, the standard deviation is somehow telling us about the width. Notice that most of the samples are in the middle. There are a few out here, but really most of them are in the middle. So that's why I'm guessing that this standard deviation is not so big. But we'll see, we'll compute it in just a couple slides. And then for Y, we have something similar. SY and SY. Okay, so those are what those quantities are. If the data is Gaussian, then there's particular meanings, like 68 points are within 68% of the points are within one standard deviation, 95% are within 2 standard deviations, and so on. Okay, so that's our guess for here. But now we can actually compute this stuff. So, so this NumPy package, like this is one of the many things it can do. And so notice that our commands, they always have np dot something. So it's like it's in the NumPy package. We're using the mean command, applying that to our vector x. And this is returning a scalar xm, which we're printing it out here, 105. So that's pretty close to what we guessed. So I'm calling SXX, SXX, that's going to be, here I'm computing the variance, So here we have the mean of x minus the sample mean, and this star star 2 is squaring in NumPy. So it's 38, so maybe I underestimated here. It's a little bit wider than what I guessed, but you get the point. So notice that there is an std command in NumPy, but I'm a little careful not to use it because, as I mentioned before, you don't know whether it's going to be the biased or unbiased version. You have to go read the manual to figure out like which one they're using. So it's just safer, simpler, and easier to just code it yourself from the basic definition. So that's why I did that. Okay. All right. Great. Any questions on anything here? Okay. So what about covariance? Let's see. Is Jiacheng Guo here?
Yeah.
Yeah. What do you think? Would you take a guess at the covariance between x and y, sample covariance?
I have to think about it.
You have to think about it. Okay. What about Kalpak Judella? Yeah. What do you think, Kalpak?
Would it be the sum from I equals 1 to, or I guess the square root of that sum, of x minus, xi minus x bar times yi minus y bar,
Great. Almost done.
and then square root of that.
One other thing about n. This is
1 over n.
1 over n. Yeah. Yeah, so it turns out we don't actually need a square root here. That's what we have. This is the sample covariance. So it's similar to variance, but rather than like x in itself, which would be variance, like it's, because remember in variance, you would have a square here and nothing there. That'd be a sxx or sx squared. This one, we're actually taking one of those x's and replacing it with a y. So this is telling us, in some sense, how related xi and yi are. It's just one sense. There's many different other senses about relationships between variables. This is just one particular simple one. The thing about this that's a little bit hard to interpret is that this grows with the size of x and the size of y. So if I double x, this doubles. If I double y, that doubles. So if I really just want to know in a relative sense how correlated these things are, then we can normalize this, and the common form is to use sxy divided by sx times sy. And so by doing this, if you make x bigger, then it doubles the numerator and denominator, and it doesn't change this overall, normalized or sample correlation coefficient. So this. Okay. So this thing, anybody guess what is the largest value this can take? 1. And what's the smallest value it can take? -1. So this is in the interval between -1 and 1. Okay, so here's some scatter plots just for different data sets, how this looks. So if you have a scatter plot like this, there's no correlation at all between x and y. So this would give you a correlation coefficient, rho xy of 0. As x and y become more positively correlated, you get something like it converges to a line with a positive slope. So this line probably, it looks like its points are maybe a little bit offline, so it's probably just a tiny bit less than 1. But now you can also have things totally correlated but in a negative way, and that would be a line with a negative slope. And then you can have things in between. Like these are pretty well negative correlated. This is -0.8, but not perfectly. So there's a little bit of uncertainty or lack of correlation, but some intuition about what that number means. Okay. Now, there's some important expressions. If we want to start doing derivation with these quantities, there's some expressions that make our lives a lot easier. So that's what I'm going to tell you about right now. So in particular, Okay, so let's start with this one. This is the variance of x as we defined it. So what I could do is I could expand this square into xi squared minus 2xi x bar plus x bar squared, right? And then I can apply the sum to each one of these terms separately, and that's where you get this. This is like the average of xi squared minus 2 times the average of this middle term. That's what this is. But because I'm essentially averaging over I, this x bar can slide out to the front. It doesn't need to be part of this averaging sum. And then finally, we have the average of x bar squared. X bar squared, it doesn't depend on I, so I'm just averaging the same thing over and over again. I just get x bar squared. Does that make sense? Okay, so let's go a little bit farther. What is this over here? X bar. Okay, so now you can see I have 2 times x bar squared, right? And so and I have a positive x bar squared, so I can combine these guys to be what? Minus x bar squared. So that is what I'm going to write over here. 1 over n I equals 1 to n xi squared. So that thing minus x bar squared. And the implication of this is that if you see a sum that looks like this, and this type of sum actually appears a lot, you just see, or let's say the average of xi squared, you know that this is the variance plus the mean squared. Okay. So it's the variance plus the mean squared. That is what the average value of xi squared is. It's important to have both terms there. Okay, so for the sample covariance, we can do a similar thing. So here's our sample covariance. We can expand this similar to what we did here. And I'm not going to go through all the details. We get a bunch of cancellations, very similar to above. We end up getting, let's see, this is xi, yi, and then minus x bar, y bar. And this implies that if you ever see a sum like this, sum of xi times yi, or an average of xi times yi, you know that this is this covariance plus the product of the two means. Okay. And knowing this stuff will make our derivations much quicker. We can just use this and simplify things tremendously. Okay, so almost done. Any questions on this? Yes.
Where'd the minus x bar squared go and the minus x bar y bar? Right before your implied, before your squared?
In the bottom part?
Yeah, in the bottom part and in the middle part.
Okay, so I definitely left out a lot of steps here. So the way you would do this is you would expand this out. You would get 4 different terms,
Okay.
right? And then you would notice that there's like the last 3 terms, there's a bunch of cancellations and they wind up all equaling this.
Yeah, where did that go into your next?
Oh, so what I did is I wrote this and I moved this to the other side,
Ah, okay.
right? So I just rearranged it. Same thing here is I have this equals this plus that.
Okay, yeah, no, I
Yeah.
see that now.
Okay, great. So, okay, any other questions on this slide? Okay, so the only thing left to do then is to sort of summarize what we said. So here we have a nice little table with some terms, notation, formulas, and what we'll typically call these in Python. So the sample mean of x, we denote that with a bar on top. The formula is just this averaging sum of xi, and in Python, call this xm. Sample variance, we can write it 2 different ways. We can write it sx squared, or as we just saw, we can write it as x double x because that is consistent. If I replace these y variables with another x, then all of this becomes identical to this. So, so we can really think about it either way. It's like the covariance of x in itself or the variance of x. The formula we said was this. We'll call this S double X in Python. Sample standard deviation is just the square root of that. Call that Sx. And then we have the sample covariance, which is this equation, and the sample correlation coefficient, which is the normalized version of this, where we divide this covariance by the standard deviation of x and y. And we know that this is always bounded between 1 and minus 1. It's nice and interpretable. You don't have to know how big and small y and x are to really interpret it. So that's it for today. Was there a question? Or?
Yeah.
Yeah.
Do those two indices on the S imply that you could, in general, create like a covariance matrix?
Okay, so we will talk about covariance matrices in the next unit. So if x is a vector with multiple terms, and I want to know like how all those different terms correlate with each other and cross-correlate with each other, then you get a matrix. So if I have like, if x is a vector with two terms, then you get a 2x2 covariance matrix. Yeah, but we'll talk about that next unit. Okay. All right, have a great weekend, everyone. See you Monday.